So coming to the outline, what we are going to discuss today, the evaporation, it is the fourth unit. Good morning. So now we are going to discuss about the introduction to evaporation, difference between evaporation and various other unit operations such as distillation, drying and crystallization. Next one, the purpose of evaporation, then selection of steam, then the boiling point and the various factors that affect it, determination of boiling point of a solution, material and energy balance. Based on that, we are going to discuss few problems, capacity and economy of evaporator, and then energy conservation techniques which can be achieved through multiple effects, vapor recompression, types of evaporators and feeding methods. Coming to the evaporation, it is a process which occurs at any temperature above the melting point. It occurs at the liquid surface wherein heat is generally added from the top. Only the molecules with higher kinetic energy can participate in this kind of evaporation process. It is a slow process. It does not involve the formation of bubbles. The process, it can be defined as it is used to concentrate a weak solution containing non-volatile solute and a volatile solvent. The solvent is usually water, and from that the product is the thick liquor which can be containing the concentrated solids. It is also a process to concentrate a weak liquor by means of vaporizing a portion of solvent. Coming to evaporation and distillation, in case of evaporation, the vapor is simply discarded, whereas in case of distillation, the vapor is going to be fractionated and it is going to be converted into useful products. Coming to the difference between evaporation and drying, in case of drying, the final product is a complete solid, whereas in case of evaporation, it is a thick liquor. Coming to crystallization, the final product is a complete crystal, whereas in case of evaporation, it is a thick solution. Coming to the purpose of evaporation. The purpose of evaporation herein involves it is used to concentrate the liquid foods, concentrate the scaly and salty solutions, corrosive and viscous liquids, energy savings in various subsequent operations, reduces the weight as well as volume, reduces the water activity, changes the flavor or else color in various products. The various products obtained from evaporation process are salt, which can be obtained from seawater, then sugar, which can be obtained from sugarcane juice, then milk can be obtained from condensed milk, and then juices can be obtained from various fruits, tomato paste can be obtained from tomato, and then hot candies from various chocolates. Coming to the choice of steam, normally in evaporation, low pressure steam can be used. The source of steam is solar energy, hot oil, fuel, flue gas, as well as electricity. The purpose of steam. The steam is playing an important role in the evaporation process. Because of the steam supply only, the product which is nothing but the thick liquor that can be obtained. The purpose of steam is, first one, to increase the temperature of the solution to meet its boiling point so that the rate of evaporation can be improved and hence the product can be recovered. Second one, to supply the latent heat of vaporization to the solvent. Then there are various factors to be considered during the feed or liquid selection. Number one, concentration. Number two, foaming. Number three, scale. Number four, temperature sensitivity. Number five, materials of construction. Number six, specific heat. Number seven, freezing point. Number eight, toxicity. Number nine, explosion hazards, and then radioactivity. So coming back to the concentration, if the concentration mainly depends upon the feed material. If the feed concentration is changed, obviously the boiling point as well as the density of the component will also get changed, and so that the rate of evaporation will be affected. We have to choose a feed material in such a way that the concentration should not be affected by any of the parameters, either heat or any of the additives like that. Then coming to the foaming, certain substances may foam out of the evaporated tube, and such a process is said to be known as entrainment. So entrainment is nothing but it is the loss of thick liquor along with the rising vapor. If the product is lost, obviously the capacity and the economy will be decreased so that the rate of heat transfer will also be reduced, which will lead to the decreased efficiency of the evaporation process. and hence we have to select the feed material in such a way that it should not contain any foaming agent. If at all it contains the foaming agent, then anti-foaming agents can be added, such as calcium sulfate or calcium hydroxide. Coming to the third one, scale. So due to long run, the tube deposits, the evaporated tubes, what do they happen means, the evaporated tubes, they tend to produce the scales, which is due to the deposition of inert materials, then waste materials, or else reaction deposits. So all these tend to reduce the overall heat transfer coefficient, and which thereby reduces the rate of evaporation also. And hence we have to remove the scale by means of adding anti-scaling agents such as wire brushers, wire scrapers, etc. Then fourth one, temperature sensitivity. Certain substances are sensitive to rapid temperature changes. So for those materials, we have to concentrate on temperature changes. For them, special techniques can be employed along with the evaporation process, such as we can carry out cryogenic condition simultaneously, so that these temperature sensitive problems can be more reduced. Coming to the materials of construction, normally in evaporation process, the materials of construction chosen is mild steel or else alloy steel can be preferable. Coming to the next one, specific heat. The specific heat of the feed material must be high such that the rate of evaporation can be greatly improved. Then coming to the freezing point of the substance, the feed material should be very low, such that it does not influence the rate of evaporation. Coming to the toxicity, explosion hazards, and radioactivity, we have to choose the feed material in such a way that it should not be of toxic, it should not be an explosive hazard, explosive, or else it should not produce any kind of radioactivity. The most common problems encountered during evaporator operation are high product viscosity. If the product is highly viscous, it may stick onto the tubes. Therefore, the expected product quality cannot be achieved, and else the product efficiency will also be reduced. So we have to take care of that high product viscosity. Then already I discussed about the high temperature sensitivity, and then the scale deposition. So that is also one of the major problem encountered during evaporator operation. So again recalling, the various factors to be considered are concentration, foaming, scale, temperature sensitivity, materials of construction, specific heat, freezing point, toxicity, explosion hazards, and radioactivity. Then the common problems can be encountered are high product viscosity, high temperature sensitivity, and then scale deposition. Then this can be a part B question. Then coming to the boiling point elevation, and boiling point and its elevation or rise. Boiling point is the temperature at which the vapor pressure of liquid equals the surrounding pressure. Boiling point is the temperature at which vapor pressure of liquid can be equal to the surrounding pressure. The difference between the boiling point of solution and that of pure water at the same pressure is known as boiling point elevation or else boiling point rise of a solution. The difference between boiling point of a solution and that of pure water at the same pressure is known as boiling point elevation or boiling point rise of a solution. Normally, the boiling point of solution will be higher than that of pure water, and hence that difference is said to be known as the boiling point elevation. So coming to the boiling point, the factors affecting boiling point: external pressure, then dissolved solids, and then hydrostatic head. Obviously, the boiling point of the solution can increase with an increase in the depth. So elevation in boiling point can be determined by using this formula, wherein ln xw is equal to lambda weight by rg into 1 by t dash minus 1 by t, where xw is equal to mw by capital MW overall divided by small mw by capital MW plus small ms by capital MS, where small m denotes either the mass of solute or water. If it is small mw, it denotes the water, and if it is ms, it denotes the solute. Then similarly, capital M, it denotes the molecular weight. Either it may be for solute or else water, whereas W denotes the water and capital S denotes the solute. XW denotes the mole fraction of water in the solution. T refers to the boiling point of pure water in terms of Kelvin. T dash denotes the boiling point of solution after the addition of solids. Rg is the universal gas constant, as you all know. The value is 8.314 joule by mole Kelvin. Lambda vaporization is nothing but it is the latent heat of vaporization of water and its value is around 2257.06 kilojoule by kg. So this value will be using in the problems. Then coming to the delta TB, it is the elevation in boiling point. It can be calculated by using this formula T dash minus T. So where T dash denotes the temperature of the boiling point of solution, TL, that is liquor, whereas T denotes the boiling point of pure water, that is obviously 273 Kelvin. Elevation in boiling point for dilute solutions, we have another formula, delta TB is equal to Kb into M, where Kb is the molar boiling constant, molar boiling point constant of solvent, and M is the molality. The molality can be defined as the ratio of number of moles of solute per kg of water, number of moles of the solute per kg of water. So boiling point elevation, again I am repeating, the increase in boiling point over that of water is known as boiling point elevation of the solution. As the concentration increases, the boiling point of the solution also increases. An empirical rule to determine a boiling point elevation of strong solutions can be given by the difference rule. The difference rule states that the boiling point of a given solution is a linear function of the boiling point of pure water at the same pressure. An empirical rule which is used to determine the boiling point elevation of strong solutions, and that can be determined using the difference rule. The rule states that the boiling point of a given solution is a linear function of the boiling point of pure water at the same pressure. Therefore, if the boiling point of the solution is plotted against that of the water at the same pressure, a straight line will be resulted. Different lines are obtained at different concentrations. The following figure shows the representative during plot for a solution. So see here, whenever the plot is drawn between the boiling point of solution and that of the boiling point of water, various straight lines are obtained. So the various denotions such as 0%, 5%, 10%, it determines the solution concentration. Solution concentration, 0% is nothing but the solution is of 0 concentration, and 5%, 5 ml of the solution with that of 90 ml of water added. Similarly, 10%, 10 ml of the solution with that of 90 ml of water. So that is the plot between boiling point of water and that of the boiling point of solution. So and from this plot, it is possible for us to determine the boiling point elevation of strong solutions. So conditions for evaporation. So the feed material depends upon the feed material temperature as well as the liquid temperature. Whenever the feed material temperature is less than the liquid temperature, if the feed is at a low temperature compared to the boiling point of the solution, obviously we have to preheat the feed so that it has to meet the boiling point of the solution, and then only the evaporation process will be carried out. So in such a case, the capacity of the evaporator tube will be obviously reduced. Whenever TF is less than TL, that is feed temperature is less than the liquid temperature, which is nothing but the boiling point of the solution, obviously the feed is to be preheated priorly so that it can meet the boiling point of the solution, and then only the evaporation process will take place. So in such a case, obviously the rate of heat transfer will be reduced, and hence capacity will also be reduced. So whenever the TF is equal to TL, whenever the temperature of the feed material is at the temperature of the boiling point of the solution, then the gradual evaporation will take place, and hence the capacity is directly proportional to rate of heat transfer. So again, whenever TF is greater than TL, that is feed temperature is greater than TL, liquid solution, the feed material will be immediately vaporized, resulting in drastic evaporation. And in such a case, the product will be immediately obtained, and it is known as flash evaporation. In such a case, the capacity is far greater than that of the corresponding rate of heat transfer. So again, I repeat, this can be the concern with too much. So whenever TF is less than TL, the feed can be preheated so that it can meet the boiling point of the solution, and then only evaporation process will take place. In such a case, the rate of vaporization will be reduced, which is nothing but the capacity will be obviously reduced. Then whenever TF is equal to TL, whenever the feed material is supplied at a temperature corresponding to the boiling point of the solution, obviously gradually evaporation will take place. That is, as soon as the feed material enters to the evaporator tube, evaporation process will start immediately, and therefore the capacity will be directly proportional to rate of heat transfer. Then whenever the TF is far greater than TL, the feed will be immediately vaporized. So in the second case, it is gradual evaporation, whereas immediate vaporization. leading to the drastic evaporation. And in such a case, it is said to be known as flash evaporation. So this can be a 2-mark defined flash evaporation. So in such a case, the capacity is greater than that of the corresponding rate of heat transfer. Then what happens during evaporation? In general, first one, the boiling point of solution rises due to the increase in solid content. So already as because of the definition, as I told in the previous definition, the process, evaporation is the process to increase the concentration of a solution. How to increase the concentration of solution? Gradually increasing the solid content. So the boiling point of solution will rise due to the increase in solid content. The delta T, that is the temperature drop between the steam and the product will decrease, and then the rate of heat transfer will also decrease. So these are the processes which can happen during the evaporation process. So coming to the material and energy balance involved in a single effect evaporator. So these are the things we are going to discuss. The objectives it is to concentrate the solute, recover the solvent, and it can be able to form the crystals. The mechanism, the heat exchange with phase change, either it can be conducted batch-wise or continuous mode. So this is the schematic representation of a single effect evaporator, wherein the feed material is given, along with that the steam supply is given. So as soon as the feed is entered to the evaporator tube, evaporation process will take place, so that the feed material can be divided, or it can be split into two parts. One is the thick liquor, which is the concentrated product, and that of the vapor. The vapor goes to the condenser, it will be of no use and it can be discarded to the atmosphere. The steam, it is supplied via the heat exchange tubes. So this is the construction of the single effect evaporator. So feed material is split into liquor and vapor. Design of an evaporation system for each effect, either it may be single effect or multiple effect. We are going to determine the steam requirement or steam consumption, that is capital S. So determine the steam consumption using the first step is mass balance, the second step is solute balance, and the third step is the energy balance. And once we have completed all the basic balances, we are going to design the evaporation by using the equation, which is nothing but Q is equal to UA delta T, where Q is the rate of heat transfer, U is the overall heat transfer coefficient, capital A is the area, and delta T is the temperature drop. By this, either the area or overall heat transfer coefficient can be determined by using the design equation. So again, I repeat, whenever we want to design a single effect evaporator or multiple effect evaporator, we are going to determine the steam requirement or steam consumption, which is nothing but capital S. So before going to determine the steam consumption, we have to determine the mass balance, solute balance, energy balance, and then we are going to determine the design by using this equation, Q is equal to UA delta T. So coming to the material balance, the overall material balance is given by F is equal to L plus V. F is equal to L plus V, where F denotes the feed supplied in terms of kg by hour, and L denotes the liquor withdrawn, that is the product, the thick product, which is in terms of kg by hour, and V denotes the vapor produced in terms of kg by hour. Coming to the solute balance or individual mass balance, F into XF is equal to L into XL plus V into XV. Since XV is equal to 0, because there is no solute content in vapor, as there is no solute content in vapor, we can obviously consider that XV as 0. So if XV equal to 0, F into XF will be equal to L into XL. So by in problems, we can determine the unknown parameter by using this equation. F into XF is equal to L into XL, where F is the feed material in terms of kg by hour and L is the thick product obtained in terms of kg by hour, and XF denotes the amount of solute or solid content in the feed, and XL denotes the amount of solute content or solid content in the liquor, and XV denotes the amount of solute or solid content in vapor. So in problems, XF will be given, or XF and XL will be given, and F will be given. From that, it is possible for us to determine the liquor composition. Once you determine the L value, you can go back to the equation 1, that is F is equal to L plus V, so that it is possible for you to determine the vapor content also. So by this, we can determine the unknown composition of liquor and vapor. Then coming to the energy balance, in energy balance, we have two methods. One is enthalpy method and heat capacity method. So coming to the enthalpy method, F into HF is equal to S lambda S is equal to L into HL plus V into HV. So HF denotes the enthalpy of feed, S denotes the steam consumption, lambda S denotes the latent heat of condensation of steam, and the value already I have given, it is 2300 to 2400 kilojoule by kg. Then HL denotes the enthalpy of liquid, HV denotes the enthalpy of vapor. So by using this, it is possible for us to determine the steam consumption. So the enthalpy values can be obtained from the steam tables at respective temperatures of feed, liquor and vapor. So through the temperatures only, it is possible for us to obtain the different enthalpies of feed, liquor as well as vapor. So once we know, so in the previous balance, in the material balance, we know about the F value. So on through that F, HF can be substituted with respect to the feed, with respect to the temperature of the feed material. We are getting the enthalpy of the feed, and through that F into HF can be substituted. Then S is an unknown parameter. Lambda is 2300 to 2400 kilojoule by kg, and then L we have got from the previous balance, and then HL can be determined by means of the liquid temperature, and V we have got by the previous balance, and HV can also be obtained from the temperature of the vapor. So by substituting or by all these parameters, it is possible for us to determine the steam consumption, that is by the enthalpy method. Once we determine the steam consumption, the area can be calculated by the next step. Then another method is heat capacity method. S into lambda S is equal to F into CPF into TL minus TF plus V into lambda V. This is the formula for without boiling point elevation. If there is boiling point elevation, the same formula can be used, but here in we are going to add the boiling point elevation with that of the TL, and then subtract from the TF. So this is how we are going to calculate the material balance steam consumption by using the heat capacity method. S into lambda S is equal to F into CPF into TL minus TF plus V lambda V without boiling point elevation, and S into lambda S is equal to F into CPF into TL minus TL plus BPE minus TF plus V into lambda V with boiling point elevation, where CPF denotes the heat capacity of the feed material, BPE denotes the boiling point elevation, liquor, TF feed temperature, and lambda V is the latent heat of vapor. So it is in between 2200 to 2300 kilojoule by kg. So there is only one difference between lambda V and lambda S. Lambda V value will lie between 2200 to 2300 kilojoule by kg, whereas lambda S value will lie in between 2300 to 2400 kilojoule by kg. So coming to the design parameter, that is the last step involved in the design of evaporation process. Rate of heat transfer can be calculated using Q is equal to S into lambda S. Also, the rate of heat transfer can be defined in terms of heat transfer coefficient, overall heat transfer coefficient, by using Q is equal to UA delta T, where delta T is equal to Ts minus TL without boiling point elevation, whereas if there is boiling point elevation, delta T is equal to Ts minus TL plus BPE. The boiling point elevation must be added with TL always. So then only it has to be subtracted from TS if there is boiling point elevation. So now equating S lambda S is equal to UA delta T. S will be determining by the energy balance. Then lambda S we know that, and then that is equal to UA delta T. In the problems, temperatures will be given. Then either heat transfer coefficient or area can be unknown. So whichever that is given, so the remaining unknown parameter can be calculated. So that will complete the evaporation problem. So this is the schematic procedure to solve the evaporation problem. Overall material balance, which is given by F is equal to L plus V. Then individual material balance, F into XF, that is equal to L into XL plus V into XV. Then it can be, the energy balance can be solved by two methods. One is enthalpy method as well as heat capacity method. Then finally design, that can be given by the S lambda S is equal to UA delta T. In problems, either area or overall heat transfer coefficient has to be determined. If area is to be determined, overall heat transfer coefficient value will be given in the problem. With respect to that, area can be calculated. Again, vice versa. So the process parameters which are getting involved in the evaporation process are capacity. Capacity is defined as the number of kgs of water vaporized for a period of 1 hour. Capacity is defined as the number of kgs of water vaporized for a period of 1 hour. Economy is defined as the kgs of water vaporized for a period of 1 hour to the kgs of steam supplied to the unit. Capacity is defined as the kgs of water vaporized for a period of 1 hour, that is simply V. And economy is nothing but kgs of water vaporized for a period of 1 hour to the kgs of steam supplied to the unit. That is V divided by S will give you the economy value. The economy is always less than 1 in a single effect evaporator. There are certain reasons for that. Number one, the amount of heat that is required by 1 kg of solution is always higher than that of amount of heat that is required by 1 kg of pure water. For example, if 1 kg of pure water requires 0.8 kg of the steam, whereas the 1 kg of solution will require nearly greater amount of steam only. So because of that, the ratio will be less than 1. That is, the amount of heat required by 1 kg of solution is always higher than that of the amount of heat that is required by 1 kg of pure water. The low pressure steam possesses lower latent heat of condensation and may be due to unavoidable heat losses. So coming to the next question, how to improve the economy? Economy can be improved by adopting various methods such as number one, multiple effect evaporation, and then employing vapor recompression technique. Vapor recompression technique. So coming to the single effect evaporator, already we have discussed about this. Then economy improvement, multiple effect evaporator. See, in single effect evaporator, the vapor is simply discarded. Whereas in case of multiple effect evaporator, see the vapor obtained from the first effect goes to the second effect, which will be acting as a heating medium in the second effect. And then the vapor which is obtained from the second effect will be acting as a heating medium to the third effect. So this is how the vapor obtained from one effect will be acting as a heating medium to the all other effects. So the vapor which is produced in one effect, it is utilized effectively without discarding to the atmosphere, and only from the last effect the vapor is discarded to the atmosphere. So herein in multiple effects, series of evaporators are arranged wherein the vapor that is coming out of the first effect will be supplied to the second effect, and that will be supplied as the heating medium to the third effect, and so on. So this is how the vapor is effectively used in a multiple effect evaporator. So on this method, this arrangement can be effectively used to improve the economy also. So that is the multiple effect evaporator. So comparison between single and multiple effect evaporator. When a single effect evaporator is used, the vapor from the boiling liquid is simply condensed and discarded to the atmosphere. This method is called single effect, and although it is simple, it utilizes steam ineffectively. For example, to evaporate 1 kg of water from a solution, it calls nearly 1 to 1.3 kg of steam, thereby resulting in poor economy. Coming to the next one, multiple effect is the vapor from one evaporator is fed into the steam chest of a second evaporator, and the vapor from the second is then sent to a condenser. The operation becomes double effect. Similarly, the heat in the original steam is reused in the second effect, and the evaporation achieved by a unit mass of steam fed to the first effect is approximately doubled. Additional effects can be added in the same manner. The general method of increasing the evaporation per kg of steam by using a series of evaporators between the steam supply and the condenser is called multiple effect evaporation. So between the steam supply and the condenser, we are going to use series of evaporators. If two evaporators are used, then it is said to be known as double effect evaporator. And if three evaporators are used in series between the steam supply and that of the condenser, then it is said to be known as triple effect evaporator. And if the number count increases than 3, then it is said to be known as multiple effect evaporation. So the methods to increase economy, second method. So first method is multiple effect evaporation. We have discussed that. Then vapor recompression technique. The vapors from evaporator is compressed to a saturation pressure of steam so that it can be upgraded to meet the original condition of the steam. So by that case, it is possible for us to improve the economy. The desired driving force in the temperature drop, in the form of temperature drop, can be created by increasing the desired driving force can, in the form of temperature drop, can be created by increasing the pressure of the vapor either by mechanical recompression or thermal recompression. So the vapor from the evaporator is compressed to a saturation pressure of steam such that the quality can be upgraded so that it can be used as a heating medium. Thereby we can improve the economy. The desired driving force can, in the form of temperature drop, can be achieved by two methods. One is mechanical method and thermal method. So coming to the mechanical method here, in the mechanical method here we have a compressor so that the pressure of the steam can be increased to a greater extent, and then as soon as the pressure of the steam is increased, then it is passed through a heater to remove the impurities, and then it is passed to the evaporator body, thereby rate of evaporation can be achieved to a greater extent. So this is the mechanical recompression method. In this method, the vapor is compressed to somewhat higher pressure by a positive displacement compressor or a centrifugal compressor. In this method, the vapor is compressed to somewhat higher pressure by a positive displacement compressor or a centrifugal compressor. Then only the vapor is fed to a heater. As the saturation temperature of vapor is higher than the boiling point of solution, immediately heat flows from the vapor to the solution. Thereby, greater economy can be achieved. More and more vapors are generated, and thereby it can improve the economy to a greater extent. Coming to the thermal recompression method, here the vapor is passed through a steam jet ejector, wherein the vapor quality can be greatly improved, and then it is passed through a heater to remove the impurities, and then the steam is passed effectively retraced in a evaporator, such that the quality of steam can be greatly improved. In this method, vapor is compressed by means of a steam jet ejector, wherein high pressure steam is used to draw and compress a major part of vapors from the evaporator, while remaining part of vapors is separately condensed for compensating motive steam added. Thermal recompression is best suited as a steam as the steam jets can handle large volumes of vapor. Jets are cheap and easy to maintain compared to the compressors. Coming to the disadvantages, low mechanical efficiency of the jets and lack of flexibility whenever the operating conditions are suddenly changed. So that is about the thermal recompression. In case of mechanical recompression, the vapor is compressed to a higher pressure by means of a positive displacement compressor or a centrifugal compressor. Whereas in case of thermal recompression method, the vapor is compressed by means of a steam jet ejector, such that the economy can be greatly improved. So coming to the, based on the material and energy balance, we can solve the problem. So I read the question. 10,000 kg by hour of an aqueous feed containing 1% dissolved solids is to be concentrated to 20% solids in a single epic evaporator. The feed enters at 25 degrees centigrade. The steam chest is fed with saturated steam at 110 degrees centigrade. The absolute pressure maintained in the evaporator is such that the water will boil at 55 degrees centigrade. The boiling point elevations are as follows. The feed 0.2 degrees centigrade and 20% solution, it is nearly 15 degrees centigrade. The overall heat transfer coefficient under normal operating conditions would be 2500 watt by meter square degree centigrade. Estimate the steam requirement assuming no subcooling of condensate, heat load on a condenser, and the heat transfer area. So, so this is the question. See here, 10,000 kg by hour, that is the feed, and it contains 1% dissolved solids, and it is to be concentrated to a XL of about 20% solids in the final product in a single epic evaporator. The feed temperature is given and the steam chest is supplied at 110 degrees centigrade. The absolute pressure maintained in the evaporator to determine the TL value is 55 degrees centigrade. The boiling point elevations are given. That is, for the liquor, it is 15 degrees centigrade, and for the feed, it is 0.2 degrees centigrade. We have to consider the liquor BPE only. So this is the schematic representation of the problem, wherein 10,000 kg by hour of the 1% of solids is supplied at 25 degrees centigrade, where the steam is supplied at 110 degrees centigrade, and the condensate is leaving the evaporator at same temperature, 110 degrees centigrade. Then the feed material consists of 1% of solids, and the liquor 20%, it consists of 20% of solids, wherein the overall heat transfer coefficient is 2500 watt by meter square degree centigrade. So let us have the following notations: PDF, concentrated product P, and water vapor V. So steam, yes. Coming to the solid balance, F into XF is equal to P into XP. So F into 0.01, 1%, so 1 by 100, that is equal to 20%, 20 by 100. F into 0.01 is equal to P into 0.2. P equal to 10,000 into, so F is 10,000. So P is equal to 10,000 into 0.01 divided by 0.2, that is equal to 500 kg by hour. So coming to calculate the V vapor, that can be calculated by F minus P, that is equal to 10,000 minus 500, that is 9,500 kg by hour. So this is the overall mass balance where we have calculated the P and V. That is, instead of L, I have denoted in terms of P and then vapor V. So by this, we have completed the mass balance. Then coming to the energy balance, So before going to the energy balance, we have to get the data from the steam tables. So temperature of water vapor leaving from the evaporator, the 55 degrees centigrade maintained at the liquor, and it is 15 degrees centigrade boiling point elevation. So summing up to that, it is 70 degrees centigrade. 104.8 kilojoule by kg in the steam tables. Enthalpy of product is 293 kilojoule by kg. Enthalpy of water vapor leaving at 70 degrees centigrade is 2640 kilojoule by kg. Enthalpy of saturated water, it is 230.2 kilojoule by kg. Latent heat of steam is 2230 kilojoule by kg. So now we are going into the enthalpy method. F into HF plus S lambda S is equal to V into HV plus P into HP. 10,000 into substituting all the values, we are going to calculate the steam consumption that can be calculated around 10,842 kg by hour, 10,842.4 kg by hour. Coming to the steam requirement is equal to, in terms of second, converting divided by 3600, it is 3.01178 kg by second. Heat load on the condenser can be calculated by using this formula, V into HV minus HW. So V is 9500 into HV is 2640 minus HW is 230.2. So it can be calculated around 6359.2 kilowatts. So coming to the heat transfer area estimation, UA delta T, S lambda S is equal to UA dt or delta T. So S is 3.01178 kg by second into 2230 is equal to lambda S is 2230, which is equal to 2.5. Overall heat transfer coefficient is 2500 watt by meter square Kelvin. So here 2.5 kilowatt by meter square Kelvin into area into 110 minus 70. 110 is the liquor temperature minus steam temperature minus 70 degrees centigrade added 55 by 70, that is TL temperature. So that is around, the area calculated is around 67.2 meters square. Heat transfer area is given by 67.2 meters square. So coming to the problem 2, which is based on the heat capacity method, a solution containing 10% solids is to be concentrated to 50% solids. Steam is available at temperature of 393 Kelvin. Feed is supplied at 30,000 kg by hour. The evaporator is operating at 323 Kelvin. The overall heat transfer coefficient is 2.9 kilowatt by meter square Kelvin. Estimate the economy on heat transfer surface if the feed is introduced at 293 Kelvin. The CP of feed is 3.98 kilojoule by kg Kelvin. So in this problem, the feed specific heat is given. If it is not given, you can assume the value of that of water, that is 4.18 kilojoule by kg Kelvin. So coming to the next one, lambda S is equal to 2202 kilojoule by kg. 2202 kilojoule by kg. Lambda V is equal to 2383 kilojoule by kg. Solution. We are going to take the basis of 30,000 kg by hour of the feed material, wherein the material balance can be given by F is equal to L plus V, and solute balance is given by F into XF is equal to L into XL. So 10 by 100 into 30,000 is equal to 50 by 100 into L. L can be calculated as 6,000 kg by hour, where V is equal to F minus L, 30,000 minus 6,000 equal to 24,000 kg by hour. And coming to the energy balance, that can be achieved through the heat capacity method. Q is equal to S into lambda S is equal to F into CPF into TL minus TF plus V lambda V. So substituting all the values, I am getting S is equal to 27,599.5 kg by hour. So we are going to determine the economy. The economy is equal to V by S. V is calculated as 24,000 kg by hour, and then the steam consumption is calculated as 27,599.5. That is equal to 0.87. So coming to the design, delta T is equal to Ts minus TL. So here there is no boiling point elevation. Therefore, delta T can be calculated directly as the difference between steam temperature and that of the liquid temperature. Ts minus TL, that is 393 minus 323, that is equal to 70 Kelvin. So Q is equal to S lambda S is equal to S 27,599.5 into 2202, that is equal to this much kilojoule by hour. And from this, we are going to equate it to UA delta T. So once we are going to determine the UA delta Q, we are going to get the area by using this equation, area equal to Q by U into delta T. So we are going to convert that kilojoule by hour in terms of watts. So when you convert that in terms of watts, so 60774099 kilojoule by hour multiplied by 1000 divided, so converting the kilojoule into joule, multiplying by 1000 divided by 3600, so that can be converted in terms of watts. So Q is equal to UA delta T. From that, it is possible for us to determine the area. Area is equal to Q divided by U into delta T. So that is around 1688, 1694 divided by 2900 into 70. That will give you around the value of area to be 83.16 meters square. So coming to a simple problem with respect to triple effect evaporator. So triple effect forward feed evaporator is used to concentrate a liquid which has marginal elevation in boiling point. The temperature of the steam to the first effect is 105 degrees centigrade and the boiling point of the solution within third effect is 45 degrees centigrade. The overall heat transfer coefficients are 2200 watt by meter square in the first effect, 1800 watt by meter square in the second effect and 1500 watt by meter square in the third effect. Find out the temperatures at which the fluid will boil in the first and second effects. Coming to the solution, we can assume that there is no boiling point elevation in the evaporators. So area of all the three evaporators can be assumed to be equal, such that A1 equal to A2 equal to A3 equal to capital A. Total temperature drop. Total temperature drop is Ts minus the temperature in the last effect. So that is given in the problem. The temperature of the steam to the first effect is 105 degrees centigrade and the temperature in the last effect is third effect is 45 degrees centigrade. So subtracting these two, we are getting the total temperature drop around 60 degrees centigrade. So the temperature drop across each first effect can be determined by using this formula. Across each effect can be determined by using these three formulas. Delta T1 is equal to 1 by U1 divided by 1 by U1 plus 1 by U2 plus 1 by U3. Similarly, delta T2 is equal to 1 by U2 divided by 1 by U1 plus 1 by U2 plus 1 by U3. Similarly, delta T3 equal to 1 by U3 divided by 1 by U1 plus 1 by U2 plus 1 by U3. So delta T1 equal to 1 by 2200 divided by 1 by 2200 plus 1 by 1800 plus 1 by 1500 into this 56. So that is equal to 15.2 degrees centigrade. So and then coming to the delta T2, 1 by 1800, that is 1 by U2 divided by 1 by U1 plus 1 by U2 plus 1 by U3 into 56, that is equal to 18.6 degrees centigrade. And the temperature drop across third effect is delta T3 equal to 1 by U3, that is 1 by 1500 and divided by 1 by U1 plus 1 by U2 plus 1 by U3 into 56, that is equal to 22.3 degrees centigrade. Therefore, the boiling point in the first effect will be Ts minus delta T1. Ts minus delta T1, 105 minus 15.2 degrees centigrade. So 105 minus 15.2, that is 89.8 degrees centigrade. So this is the temperature at which the solution will boil in the first effect. Similarly, the boiling point in the second effect will be calculated by using this formula Ts minus delta T2. So that is 89, sorry, that is not Ts, that should be delta T1, TL1 minus delta T2. So TL1 is equal to 89.8 from we have calculated that from the previous step. So 89.8 minus 18.6, that is 71.2 degrees centigrade. So this is how we are going to calculate the temperatures at which the solution will boil in the first effect and second effect. First effect Ts minus delta T1 and second effect it is TL1 minus delta T2. So coming to the types of evaporators, so there are various types of evaporators, natural circulation and forced circulation evaporators. Natural circulation evaporators are of various types again. Open pan evaporator, horizontal tube evaporator, short tube or calandria evaporator, and then long tube vertical or falling film evaporator. So there are four types of natural circulation evaporators. Open pan evaporator, horizontal tube evaporator, short tube or calandria evaporator, then long tube, vertical or falling film evaporator. So coming to the second type, forced circulation evaporators, wherein the evaporation is forced by means of an external heating element, or either it can be installed horizontally or vertically. So if it is horizontal, then it is horizontal external heating element, and if it is vertical, it is vertical heating element. So this is about the classification of the evaporators. Natural and forced circulation evaporators. In natural only, we have four types: open pan, horizontal tube, short tube or calandria evaporator, and long tube vertical or falling film evaporator. In forced type, we have two types, one with the horizontal external heating element and the other with vertical heating element. So coming to the general description for the evaporators, it consists of a long tubular heating element which consists of a bundle of tubes, and the tube bundle can be about 150 centimeter high and the tubes are of 50 to 100 mm in diameter. Then the vapor space. The vapor space removes the entrained liquid from the vapor. The vapor outlet removes the vapor from the top of the tubes. There will be a return pipe which is used to provide the natural circulation of the unvaporized liquid. And then steam chest, it is used to supply the steam to carry out the boiling of liquid inside the tubes. And the baffles will be provided within the tubes in order to provide the uniform distribution of steam. The central downtaker, which is used to provide the circulation of cold liquid. Normally, the steam will be supplied outside the tubes, and inside the tubes, the feed material will be passed through. The feed will be passed through inside of the tubes, and outside the steam will be supplied so that evaporation will take place. So in case of short tube Calandria evaporators, the purpose of short tube Calandria evaporators, it is suitable for clear liquids, non-corrosive liquids and mild scaling solutions. It is suitable for clear liquids, non-corrosive liquids and mild scaling solutions. And then coming to the falling film evaporator, it can be used for foaming liquids, corrosive solutions and large evaporation loads. Foaming liquids, corrosive solutions and large evaporation loads. So this is about the various types of feeding methods in multiple effect evaporator. So in multiple effect evaporator, we have different kinds of feeding methods: forward feeding, backward feeding and parallel feeding. So coming to the forward feeding, see here, the feed will be supplied in the first effect. So that is forward feed, wherein the inlet, see here, the inlet denotes the feed entry. Wherein in case of backward feed, the feed will be entering at the backward direction. So as you move from one effect to another effect, the order of pressure will be in the form of decreasing order. In case of forward feed, the first effect will be at a high pressure, then here low pressure and here lower pressure. And since the liquor that is obtained from one effect to the another effect, it is taking place at a decreasing pressure, it does not require the installation of the pump here. Whereas in case of backward feeding, see here, already I told you, in the pressure will be high in the first effect, then it will be in the lower order, decreasing order. So in such a case, in backward feed, the feed is entering at very low pressure. The feed is entering at very low pressure in the last effect. So to transfer the liquor from one effect to the another effect, whenever you are going to transfer the liquid from in the pressure or in the increasing pressure order, we have to install additional pumps. So here pump arrangement is required such that the transfer of liquid can be taken place. So this is the difference between forward feed and backward feeding arrangement. See, in forward feeding, there is no arrangement of the pumps because the liquor is sent from one effect to another effect in the decreasing pressure order. Whereas in case of backward feeding arrangement, here the liquor is to be transferred from one effect to another pressure in terms of increasing pressure order. So here high, here low and here lower. So whenever it is lower to that is somewhat high value, we are utilizing the purpose of the pump here. So through the pump, we are going to transfer the liquor. Additional cost must be spent for the backward feed arrangement for the installation of the pumps. So this is the major difference between the forward feed arrangement and the backward feed arrangement. Then coming to the parallel feed, see here in inlet is given in the first effect, then the product is obtained via the pump and it is transferred to the second effect. So from each effect you can withdraw the product. From each effect you can withdraw the product. So that is the difference between forward, backward and that of parallel feeding. So in case of forward feeding, you are going to get the thick liquor only by means of the last effect, Whereas in case of backward feed also, you are going to get the final product only from the last effect. Wherein in case of the parallel feeding arrangement, here we are going to withdraw the product in each of the effects. So whenever we want a product in higher amounts, suppose immediately we want to manufacture nearly some 500 kg of the product, means within a shorter period of time we are going to produce a greater quantity of product, then we can go with the parallel feeding arrangement, wherein the product can be availed from each of the effect such that it can be combined to give the overall product. Whereas in case of forward feeding and backward feeding, only the final product will be obtained from the last effect only. So in case of forward feeding, it can be obtained from the third effect, whereas in case of backward feeding, it can be obtained from the first effect. One more difference between forward feeding and backward feeding: whenever you want to evaporate the viscous solution, the backward feeding arrangement can be recommended, because in case of third effect, the higher temperature can be, pressure is of decreased order, where the temperature will be bit higher in the third effect. So whenever you're going to make the viscous liquid to meet the higher temperature in the last effect. So in backward feeding, this will be the last effect, and whenever the feed material want to meet a higher temperature, this kind of backward feeding arrangement can be recommended. So that the product is viscous, then it can be treated in the last effect, and from that the product can be recovered. So this is the difference between forward feeding and that of backward feeding. So in case of forward feeding, the pressure is of the decreasing order, and that's why we are not installing the pump here. Only for the last effect, we have a pump here to transfer the product from the last effect. Whereas in case of backward feeding arrangement, we have the pump installation in each and every effect, because the feed material is to be transferred in the order of increasing pressure. So because of that, we are utilizing a pump in each and second and third effect. So from that, we can recover the final product from the last effect. Then in parallel feed, the thick liquor that is produced from each and every effect, that can be consolidated to form the final product. So that is the difference between forward feed, backward feed, and parallel feeding arrangement. So thank you. This finishes